So last time we ended around about here. Right, so I had just quickly told you about the utility of luminosity or mass functions of galaxies. Uh, so some of you guys who have worked on galaxy formation must have encountered this. This is a very important plot, which shows the importance of this one of the center pieces of modern understanding of galaxy formation, so-called feedback. Right, that supernovae and AGN can affect star formation efficiency globally within a halo. Okay. We also talked about this thing called surface brightness, which is an inherent property of diffuse sources like galaxies. And if you put the galaxy far away or nearby, surface brightness remains the same. So it's sort of the integrated light along the line of sight. And it's just the flux divided by angle squared, right? And the distance factor in both terms sort of cancel each other out. Okay. So so these are some examples of measured surface brightness from nearby galaxies. Right. So, for example, here, so this is I band magnitude. So this is this is I band. So the surface brightness measured in I band. The units are magnitudes per arc second squared, right? Remember, this 27 magnitude per arc second squared is roughly 1 solar luminosity per parsec squared. So that's a good thing to remember. If you remember that, you can actually convert from one to the other. A more intuitive thing is solar luminosity per parsec squared, but more common is this magnitude unit. And last time we showed that this 27 and solar luminosity per parsec squared are sort of mapped to each other. So let's look at this surface brightness profile. This is a galaxy called NGC 7331. The solid line shows the surface brightness in I band near 8,000 angstroms. So it's sort of infrared band. The dashed line is an exponential. So this dashed line, which fits the outer part pretty well, is an exponential, right? So it's a log linear plot, right? Or for surface brightness as a function of distance from the center. So a straight line on a log linear plot is an exponentially falling. So y equals e to the minus x will show a straight line like this. So this is an exponential disk. Normally, the exponential surface brightness profile corresponds to disk galaxies, spiral galaxies. Whereas the central part is much steeper and the surface brightness value is higher. And so this is the so-called bulge. So every galaxy you can actually decompose into a bulge and a disk. And a pure elliptical galaxy is something which has very subdominant disk, and a pure disk galaxy is one which has a very subdominant bulge. But in general, you have both components. So the bulge can be thought of as a little remnant of elliptical galaxy at the center of a disk galaxy. So I've actually retained the captions here because the captions in the book, even if you don't read the text, look at the figures, read the captions carefully. They can almost independently be understood. If you just come to the class, if you look at the figures and think a little bit about them, you will gain quite a good understanding of what I'm talking about. But it's good to read the book as well. So this is along the major axis. So if you have a you know, let's see, did we talk about these isophotes? So so let's actually talk about these things. What are these? These are curves of constant surface brightness as a function of angle in 2D. So you look at a galaxy and draw these curves of constant surface brightness. Okay, these are called isophotes, right? The curves of constant surface brightness of an image of a galaxy are called isophotes. So the inner ellipses or circles or these inner contours correspond to higher surface brightness, and the outer ones are dimmer. And as I mentioned, just outside the center, the sky is brighter than actually the galaxy. So you have to really do subtraction and do all that in order to recover the true brightness distribution. So once you have this, then what you do is, okay, let's say this guy, you go along the major axis and make a plot of surface brightness as a function of distance. So this is what that is. This is, if you have an elliptical galaxy or an ellipse on the sky, this is you go along the major axis and just plot that contour, the values on the contour plot along that line. This is that intensity as a function of radius, okay? And this HR is something like for a disk galaxy is for an exponential galaxy, e to the minus r by HR is something like how the surface. So HR is the scale height for the exponential disk. So by at what distance from the center does the surface brightness fall below? I'm recording, right? Okay, cool. Below, falls by 1 by e. Okay, now so this is a composite galaxy which has both a bulge and a disk. This is another example of a galaxy which so these dots are our data. These dots actually do a very good job, are actually well fit by this n equal to 1. So I'll actually tell you what. So this is what the n is that I'm referring to. So n equal to 1 is just an exponential disk, right? E to the minus r by r naught. N equal to 4 is intensity going like e to the minus r by r naught to the power of 1 by 4. That's a very famous profile, the so-called de Vauquelins profile, that's used to fit elliptical galaxies and bulges. So here we are showing a de Vauquelins profile and a disk sort of expected from the disk, and more or less disk does a good job, but there is like an envelope which perhaps sort of shows that there is a little excess. So as you compare the exponential and the n equal to 4 profile, there is for n equal to 4, there is excess both at small radii and at large radii. Okay, so it's a good idea to sort of have a feel for how these simple functions look like.
Why is there excess brightness at like ends of the galaxy?
So the elliptical galaxies are actually very diffuse. So I mean, and the central part is very bright, but they also have very diffuse distribution of light. So that's just an observational fact. And it's sort of the distribution of stars, their positional distribution and their velocity distribution actually tells us a lot about the process of galaxy formation. Galaxies, the stars in the galaxies are collisionless objects, unlike gas, which is collisional. So if you have a collisionless system, they do not forget about their initial conditions. For example, if I give you a gas at some density and temperature and ask you where were the molecules at T equal to 0, it's impossible for you to tell because they have shared their energies, momenta, and so on. Whereas stars, being collisionless, they do get sort of moved in complicated trajectories in the phase space, but they do retain memory of how they were born, being collisionless. They don't relax to some sort of a Maxwell-Boltzmann distribution. Okay, so it's important. So all these complicated things like appearance of these isophores, velocity, dispersions, and so on, tell us about galaxy formation. How did a particular galaxy evolve into what we are seeing now? Okay, so this so this is about this. This is a dwarf elliptical galaxy, actually. So it does not have a very central, very bright bulge, but it does have this envelope which is extended. So this DE here corresponds to dwarf elliptical. And the luminosity is about 10 to the 8 solar luminosities. Our Milky Way's luminosity is about 10 to the 10, 2 times 10 to the 10 solar luminosities. The brightest CD galaxies can be 100 times brighter than the Milky Way luminosity. So the range in galaxy luminosity is large, but not very large. The dimmest galaxies would be 10 to the 6 or 10 to the 7 L sun. 10 to the 7 L sun to 10 to the 11 L sun, which is smaller range than the mass distribution of dark matter halos, for example. So a key question would be, why are galaxies forming in this narrower mass range? And it has to do with this feedback that we were talking about in the previous slide. These are some general functions. I mean, this is a plot of surface brightness as a function of radius for different values of n. So this is a log plot. So you have to be very careful when reading the axes. So this is log linear plot. This is a log plot. So they will look different depending on how the axes are. So this is an n equal to 1 disk. Right, so it remains below. So they are adjusted. I naughts are adjusted so that they are equal at r equal to r naught, right? And you see the n equal to 1 is sort of distributed broadly, more diffuse way at small radii, but at large radii it's more compact, sort of like this, what I was mentioning here. And as you increase your n, they become centrally concentrated, but they also have these diffuse envelopes. These are called Cirsic profiles. Okay, and these are also commonly used for fitting surface brightness profiles of observed galaxies. And n equal to 4 here is this D Voculus profile, which is commonly used for elliptical galaxies. Okay, so what I'll do now is, so we talked about this morphological classification of galaxies the last time, right? Teams. And we said that it just depends on how the isophores of this galaxy appears is what determines whether it's an elliptical or spiral and so on, right? So that must depend crucially on the viewing angle, right? For example, if you have a just a second. If you have a disk galaxy and if you're sort of viewing it edge on, it appears very different from a face on spiral galaxy or a disk galaxy, right? So similarly, if you have an elliptical galaxy, say a spheroidal galaxy, which has two equal minor axes, say an oblate spheroidal, which has two major axes. So it's sort of like a disk, right? In some sense, so two long axes and the one short axis, and the axis of symmetry is along the short axis, right? That's oblate. Oblate is like our Earth is an oblate object. Similarly, Idli is an oblate object, right? So the question is, how does the observed oblateness tell us about the intrinsic axis ratio of these ellipses? Okay, so what we are going, we are going to study elliptical galaxies now, in this class, and then we'll actually switch to spirals next time. But all these isoforts and all these things are used for all galaxies, and this is called the photometric study of galaxies. Okay, because you're taking images essentially. So here is actually the problem. Uh, so let's see, what's the topic? Uh, so so effect of projection uh, projection of a spheroidal uh, galaxy. Okay, spheroidal. I mean, in general, the elliptical galaxy you can model as a triaxial ellipsoid. So you imagine an ellipsoid, and the three principal axes have different sizes. Okay, but here we are considering a spheroidal galaxy, and the first case we'll actually do is an oblate spheroidal. Okay, so for an oblate spheroidal, anyway, the equation of the ellipse is right. So let me just write, so m squared equals x squared plus y squared by a squared. So x and y directions are along the long axis of the spheroid, plus z squared by b squared. So so if you look at this guy, and if you look at this, the projection in the x z plane. So this is x and this is the z. So z is the axis of symmetry, right? Because it's equal size in the perpendicular direction. So this is how the ellipse. This is how, say, the ellipse looks like, and and if we are seeing this from some inclination angle I, so this is the direction of line of sight. Okay, so if you have this, yeah. Right. So let me actually, yeah. So m, so the mass contours, so the contours within which mass is m. You can actually think of this. So mass or density, number density. Uh, so total number of stars within x, y, and z is a function of m. So basically, the 3D the contours of constant mass are these oblate spheroids, right? So m is like a label. So as you go inside, m is 0, and if you sort of go out, m increases. You can actually think of this as that. So the other thing that you can actually assume is mass is proportional to light, right? And it's sort of, if you had the same initial mass function, that's actually true, right? You have the same population of stars everywhere. That's sort of a good zeroth order assumption. Okay, so this is the inclination angle. This angle. So this angle is known as the inclination angle I. Okay, and this is the observer. We are looking at this angle, and so if we have such an oblate thing, and we are seeing it from the top, right? You will just see a circle, right? If you see it from the side, you see an ellipse with major and minor axes, capital A and capital B, right? So so for an oblate thing, A is bigger than or equal to B. And there are two major axes in this case. Okay, so let's see. Let's look at geometry a little bit. So if you're viewing this disk at some angle, not like this or not like this, how does it look like in projection? It appears like an ellipse only, but its apparent axis ratio is different from its true axis ratio, right? Because you can go from like ellipse with the true. So when you look at it like this, edge on, you see the true axis ratio. If you look at it face on, you see that it's a circle. So in general, the axis ratio, the observed axis ratio will be smaller than the true, so the apparent B by A will be apparent B by A will be larger than the true B by A. This is the tangent point, right? This is a point which is tangent to this ellipse as seen from the observer. And what we want to know, so the apparent, right? So this is uh, this is a disk that we are viewing. Now we are at this angle, and we want to know the size of the. So the major axis of this will remain the same, right? Which will be this, because it's sort of the longest side will still remain the major axis, but the short side will depend on the inclination angle, right? Because from here to edge on to face on, you can see it. So this basically so this is a tangent, right? This length. So let me actually mark. So this is O. This is this point T is the tangent point. This is R. This point is R. This angle is, of course, the inclination angle, because these two are parallel. And this is the length we are after, right? This is the apparent, apparent minor axis of the ellipse. Okay, so let's just do the coordinates are xt, comma yt for the tangent point, and this line, the tangent line, we want to know what's the equation of that line, right? The equation of this line is nothing but, it's actually very simple geometry. So the equation of this line is z minus zt, sorry, x comma z, it's not y, because we are looking at xz axis. So as z minus zt by x minus xt equals cot I, right? Because I is this angle, so this angle will be 90 minus I, so tan 90 minus I is cot I. So cot I, and this is also equal to, right, the derivative at that point on the ellipse. So this is also equal to dz by dx as measured at point T. Okay, but this point also satisfies the equation of the ellipse. So xt squared by a squared plus zt squared plus b squared is equal to m squared. Right? So we are looking at y equal to 0 plane. Okay, so and on this ellipse, we can actually, right? So any point on this ellipse satisfies it. So if we do the derivative at that tangent point, we get, we can actually calculate dz dx from the equation of ellipse. We can actually calculate dz by dx evaluated at that point. That's nothing but minus xt, and basically I'm differentiating the equation of the ellipse and plugging in x equals xt and z equals zt. So minus xt by zt times b squared by a squared, and that's equal to this cot I, right? Because the local derivative here has the same slope as this line, tangent line. Okay, zt, right? So this is it. So now we have, so 1, two equations. So actually, these two equations. So when actually combine, so actually three equations, right? So we can actually combine them to obtain, we can actually obtain, okay, this point is point Q. We can obtain the distance OQ. OQ is nothing but the coordinate, the Z coordinate on the uh, x equal to 0 axis, right? Here, for example, if you substitute x equal to 0, so Z equals ZT minus XT cot I, right? So that's ZQ, let's call it ZQ, right? And if we, so from these two equations, equation 2 and 3, if we plug in xt in terms of or zt in terms of xt, we can actually solve for xt in terms of zt or vice versa. So then distance OQ, so OQ is actually equal to, which is nothing but ZQ is equal to ZT minus XT, and cot I is this guy from equation 2, so minus XT by ZT B squared by A squared. Okay, and this is nothing but we can actually see that this is xt squared by A squared plus ZT squared by B squared, which is nothing but M squared. So if we do all those plugging in, we get M squared times B squared by ZT. So we got this distance OQ. Now we want OR, right? OR is the apparent minor axis value. So that's nothing but OQ times sine I, right? So B, the apparent minor axis is equal to OQ times sine I, and that is what? So we have this M squared by B squared ZT times sine I. So M squared B squared by ZT times sine I. Okay, so we have the, we have the B value. A value is the same, right? Because projection does not change the major axis for this oblate spheroid. So we can also solve for ZT in terms of M and B, from these equations. So ZT equals MB squared A squared cot squared I plus B squared to the 1/2, right? So it's actually just like simple algebra. So let me actually write down the final result for Q. Q is the apparent axis ratio. Q is defined as B by A, right? B is the apparent minor axis value. So if we plug that in, what we get is equal to B squared by A squared plus cot squared I, the 1/2 times sine I. Okay, let's see if this makes sense, right? When I is, okay, we can actually simplify it further. We can write in terms of sine and cosine. So this is, so, this implies B by A squared is equal to capital B by A. So remember, capital B by A is the true axis ratio. Small b by A is the apparent axis ratio squared sine squared I plus cos squared I, right? So so you just square it, and cot is sine by cos by sine. So when I is equal to 0, that is if you're seeing from top, the apparent axis ratio should be 1. So if you put I equal to 0, it does give you 1. If I equals pi by 2, you're viewing it edge on, uh, it gives you b by a. So it gets the limits correctly. So this formula, anyway, we derived it, it's correct. And I have the expression here. So I mean, algebra is extremely simple.
How you are getting equation 3 for
Equation 3, let's go back. Where is equation 3? 1, 2, 3. This is just the equation of the ellipse, right? X squared by a squared plus z squared by b. So this point, tangent point T, lies on the ellipse. And the equation of the ellipse is this, right?
The expression for the CT at the bottom.
Uh,
The left side bottom.
this one,
Yes.
right? Uh, right. So there is so this is a relation between xt zt. This is a relation between xt zt. So there are two equations, two unknowns. You just solve it. Okay. So I've not given all the steps, but it's actually simple algebra.
It's just because dimensionally.
Oh, let's see. Is it not dimensionally? It's correct, right? So oh, okay. So maybe then I have. Oh, yeah. This is minus a half. That's why it does not make sense. I'm sorry. Ooh. Yeah, good. Yeah, if you look at these, see, I mean, this maths can be done at home. If you pay attention here and, help me prevent making mistakes. This is like almost 10th grade coordinate geometry, nothing more than that. Okay. And we can actually then write it as, so Q, this axis ratio is called Q, so Q squared oblate is equal to, so we can write it as b by a in a different form, b by a squared plus cos squared I times 1 minus b by a, the whole squared, right? Since this is an oblate spheroid, b by a is less than 1. So what this means is this is greater than the true q true square, right? Because this is a positive quantity. So, and q true is just b by a. So, I mean, it's expected, right? The apparent axis ratio or apparent uh, this ratio of minor to major axis will be less than the true value. It's sort of also intuitively obvious. Because a lot of times you'll see like axis ratio close to 1. Okay. So eventually, why are we doing all this? Because what we'll do is our surveys have given us millions of, or at least thousands of nearby elliptical galaxies. What we'll do is we'll measure the statistics of apparent ellipticities and try to see whether they are consistent, uh, whether they can tell us about their true distribution of capital B by A. Right. So that sort of is the idea. That's why we want to do it, because the observable thing is small b by a. What we are after really is the actual three-dimensional shapes of the isophore, contours of constant mass. Okay. Uh, if you have, instead of oblate, if you have prolate spheroid, prolate spheroid is like a, what's an example of a prolate spheroid? Yeah, sort of. American rugby ball, right? A prolate thing, or the American football. That's sort of a prolate thing. Prolate means that it has two minor axes and one major axis. Oblate was two major axes and one minor axis. So it's sort of like a cigar, right? That's another, cigar is long. It has two, it's like a cylinder, but it's sort of a long thing. Okay. So prolate spheroid. In this case, A is less than B, right? So right. So A is less than B, meaning it has two minor axes. So in this case, what do we have? We have, I mean, this algebra just goes through exactly because, except in this case, the projected uh, axis will be longer than the minor axis, right? If you sort of see this at any angle, the small axis will remain the same because of axis symmetry, but the long axis is what will change. Okay, so the algebra actually just falls through, but the definition of Q in this case, Q is defined such that it's always less than 1. So in this case, the definition of Q is A by B, not B by A. So this is equal. So if it's in fact the expressions are identical. So A by B squared is equal to. So basically this expression, inverse of that expression. So it's exactly the same actually. B by A squared sine squared I plus cos squared I to the minus 1, right? It's the same expression. It's just the inverse of this that we call the axis ratio. So this thing will also be greater than equal to A by B squared, right? Even in this case, right, the major axis will be smaller than the true. The apparent major axis will be smaller than the true major axis. So A by B is greater than or equal to the true A by B. So in both cases, you in this projection, you are underestimate. You are your Q is larger than its a true value, right? The apparent Q that you measure is larger than the true value of the axis ratio for this particular case. Doing this in 3D is actually harder. This geometry and all that becomes harder. And in fact, what you can actually do is do projections, like you can do it sort of numerically. But this is just to give you an idea. Okay, so how this thing works. Okay, let's see. Yes.
Is it possible to measure eye observationally? Like if you're looking at basically you're looking at a projection. Looking at that, can we estimate eye?
Not in general.
Because we can only measure.
Yeah, you cannot So if you see a circular projection, a circle as projection, it may be that you're looking at a cigar from the axis, or it's actually truly, I mean, it's a sphere, right?
So from small a by b, possible to estimate. So you are saying that we want to know the actual a by b.
Right. So for a single case, it's not possible. But if you assume that the line of sight angle and the orientation of these principal axes are random, you look at the distributions, then you can actually figure it out. So that's where we are going, actually. Good question.
So shouldn't the A by B values be related to the angular momentum?
Yeah, they are. So if your A by B is, I mean, if you're like if you're an oblate system, you have higher rotation in general. That's correct. But here we are like, we're not talking about dynamics. We're just, just doing, geometry essentially.
But
Okay.
when we look at large distribution, certain regions may have a preferential angle.
Oh yeah, that's right. Absolutely. So like disk galaxy or the more uh, smaller b by a have more directed angular momentum. Like, okay, let's see how we use the distributions. What's the time cycle? Okay. Okay, so let's look at let's assume, so this, let's talk about distributions of Q, right? So for a given B by A, we are sort of thinking about how do the number of galaxies with the given, between Q and Q plus DQ, how does it vary? Okay, so uh, let's call F, and let's assume a oblate case, okay? If we assume oblate, that they are sort of more uh, disk-like, and that's actually true. Most galaxies are oblate rather than prolate. Okay, so let's assume oblate, and let's call it F oblate Q delta Q. So let's understand what this is. So F oblate Q delta Q is the probability of the apparent axis ratio lying between Q and Q plus delta Q. Okay, and if we assume the inclination angle to be isotropic, right? There is no reason along the line of sight you will have, preferred orientation of the elliptical galaxies are expected to be randomly oriented relative to the line of sight. So then this should actually be equal to sine I di, right? Right. So the number, so if the angles are, this is nothing but the solid angle, right? When you are x, so when you look at the volume element in spherical coordinates, right? It's uh, sine theta d phi r d theta dr. So it's sort of that thing. So sine theta d theta. Yeah, I is like a theta. Okay, and theta has uniform distribution. So this is the number of galaxies will be proportion between I and I plus di will be proportional to this. So we are assuming then to be isotropically distributed. There is no preferential orientation. Okay. And so this is nothing but, so we know Q is just a function of I, right? You can actually see for a given B by A, Q and I are functions of each other. Essentially, you can go from one variable to the other. So this is nothing but sine I times uh, uh, dq by di, and we'll just put a magnitude here, times delta q, right? This is nothing but this. This is a change of variable. So your fq is nothing but quantity, right? And given the expression of q in terms of I that we have here, for the oblate case, this one, given this, we can just do this, dq by di. So let me just write down dq by di is equal to sine 2I by 2Q times B by A. So we are assuming B by A to be fixed. It's capital, we are assuming that all the galaxies have the same B by A for this exercise. So B by A the whole squared uh, minus 1. If you do the algebra, this is what you'll get. Uh, but you want to actually, when you're writing this as FQ, you want to plug I in terms of Q, right? This is not FQ. This is the correct value of FQ, but you want to write that I in terms of Q. That's when you have FQ. So that can also be done. And let's see. Right. So from this kind of expression above, for the oblate case, we can actually write uh, cos I is equal to Q oblate squared minus B by A squared, square root of that divided by 1 minus b by a squared. So again, consistency check. When I equals to 0, Q of blade should be 1. Yeah, which makes sense. When I equals pi by 2, Q of blade is b by a. So yeah, so that sort of makes sense. Okay. Now what we'll do is, this is twice sine I cos I. If you plug in that sine to I in terms of b by a and q, you will get fq. Okay, so let me just write down what fq is. So that fq is equal to, let me also write oblate here, q by 1 minus b, b by a the whole squared, square root of that, and q squared minus b by a the whole squared, and again a square root of that. Okay, so this is the distribution function that you expect. So now this is what you should compare with the observational distribution. So you observe, say, 10,000 galaxies. You measure their Qs, right? Make bins in Qs and see what the distribution function looks like. Then you compare with this function. So how does this function look like? So we just want to know how this function looks like. Actually, it's sort of easy to see. When Q goes close to b by a, it sort of blows up. Right? It's like 1 by square root of x near x equal to 0. That's how it behaves like. So let's see. Let's just draw a schematic function that looks like, f q, f oblate, the observed q versus q. Of this is true value of b by a. So you cannot observe anything which has a b by a less than this, right? So the distribution function on this side has to be 0. We know that. So, and here this distribution function blows up. It sort of looks like, it almost becomes flat. Okay, and it's sort of, if you go very far, if q is and of course q cannot be bigger than 1 by definition. So at q equal to 1, that's just 1 minus b by a the whole square. So that's sort of this is the general shape. Okay, so now what you want to do is actually compare the observed distribution with something like this. For example, if you find that in a place or a galaxies of a certain kind do not show these apparent axis ratio smaller than a certain value, that means that true b by a will have to be larger than that, right? That's sort of an obvious conclusion of this. Okay, so this is about it. So now I want to go back to my slides where we were. So this is clear, right? What were we doing? No.
Is it necessary for a region to have b by a ratios not less than a particular value? Why can't there be spherical galaxies?
I mean, you can have. That's true. But if we look at the distribution, we'll actually get a sense of how rare are those or how common those are. So you select samples. So galaxies which have similar luminosity are in similar neighborhoods, surroundings, and have similar sizes, are generally lying, show similar PDFs. Okay, distribution functions. Okay, let's see. Just a sec.
Because
Here that we have derived this is like kind of idea, like so people can define their own PDFs also from the
Yeah, I mean, yes. So, so I was actually going to show you this real observed data. Yeah, yeah. Gaurav.
F blows up when Q is close to P by A, does that mean that we are extremely likely to actually observe
That's correct.
true ratio?
That's correct. So you have a good chance of observing the true B by A value. So wherever it actually, if the distribution is like that, so here there are a lot of ifs there. Capital B by A being constant is a very strong assumption, right? You'll have a distribution of capital B by A. So you cannot like take this very literally. It just sort of gives you an indication. For example, here is observed access ratio and B magnitudes for elliptical. So on the towards the right, brighter galaxies, towards the left, dimmer galaxies, and there are like these filled circles and the open circles. The filled guys are in general brighter, right? They are on the right part of this graph, and their sort of apparent axis ratios are that uh, they have actually a higher value of true B by A, right? Whereas these more diffuse guys have a lower value of the true axis ratio. Uh, so, so what it means is that the brighter galaxies are more, uh, more spherical, closer to spherical than the dimmer diffuse galaxies. Okay, so these are just the data. These are individual galaxies. Okay, the dots are individual galaxies. But if you use the numbers and try to draw contours of constant uh, probability, that's how it would sort of look like. It's some sort of this is like a kernel estimate. Given like the number of people with a certain height, what is the PDF? So going from actual distribution to the PDF is what is done here. And this is that thing that we were talking about, this FQ. So few of ellipticals appear circular on the sky. You see, for example, here, there are not a lot of these dots close to 1. Right? It should become flat as you go from B by A, true B by A to the larger values of Q, it should become flat. But you go here, the number of circles is actually smaller than what you expect. So what it means is that this model of oblate spheroids actually is not quite correct. And the true distribution are not these spherically symmetric prolate or oblate systems, but in general triaxial. The 3-axis ratios are different. So by looking at these kinds of things, you can get some sense of their true axis ratios and things like that. Okay, let's go back to this. No. This is for the next class, lecture 4. Okay. So we were talking about this. Okay. Now, elliptical galaxies are actually quite complex. Although they may appear to be like very nice, smooth looking, they are very complex in general. So these are like 4 examples of these isophores that we were talking about. So you see, these are almost circular isophores for A. For B, what you'll notice is that the inner isophores are horizontal. Right, the major axis is horizontal, whereas at larger radii it becomes vertical. So this is called the twist of the isophores. So the inner ellipses are horizontal, but the outer ellipses become sort of vertical. This is another complicated isophore. So you see here there is deviation from an ellipse, right? They're more sort of narrower, they're like thinner than an ellipse would be. Right? These are called disky isophores. So they have if you have disk-like systems, they will have isophores like this. They have axis at the major axis. These are also deviating from ellipses. Right? These curves they are more box-like compared to an ellipse. So these are called boxy orbits. So these, yeah, and different types of galaxies are like the boxy orbits are boxy isophores are seen in massive galaxies, massive elliptical galaxies, giant ellipticals, whereas these disky isophores are seen in galaxies which have disk component, right? So like a CD galaxy, for example, central dominant S0 galaxy. Uh, a disk. Right, so disk would be similar to this. It becomes more disky, it's sort of.
Would be the orientation.
Oh, what would be the orientation of the disk? So, right, so it's the disk's major axis will be along this direction. Okay, so this is anyway an example of this surface brightness as a function. Radius. So it's very important to pay attention to the axis of these figures. This is r by re to the 1/4. Previously, if you were looking at these profiles and they were r by re, sometimes linear, sometimes log. This is linear, but in r by re. So on this axis, you expect it to go like y equals e to the minus x, because now it's x is chosen differently. So on this axis, you should expect a straight line. It's a log linear plot. So the straight line here would be an elliptical d Vauquelins fit to an elliptical galaxy. So this is an elliptical galaxy, and it sort of looks like a good exponential fit. The inner part is sort of becomes a core. It becomes horizontal, and part of this is because of this thing called seeing that we were talking about. That if you are looking through a turbulent atmosphere, a point source gets spread over an angle, and this angle is is because of that. So if you had a point source like a star, and if it was in that direction at that time, the size of that star would be this big, essentially. So that's why even though inside profile may be steep, it actually appears to be flattened because all that light which is centrally concentrated has been spread out. Okay. So this is a normal elliptical. This is a CD galaxy. So CD galaxies are these S0 central dominant S0 galaxies which have both a bulge, a massive bulge, and a diffuse disk. And here you see there is an extra, right? It's not an exponential in r by re to the 1/4. There is like extra component, which is the disk component, right? Over and above this straight line. So that's like the diffuse part. So this is an industry in itself, trying to do these fits. This is another example. So you see a negative image of faint arc-like shells around elliptical galaxies. So this is an elliptical galaxy, and what you've done is you take an out of focus image and take this out of focus image is basically a smoothed image, and if you subtract them, you enhance these features, right? These are some sort of shells in stellar density, and these are understood to be some sort of remnants of a merger or something. Right? So you have excess density of stars here. This curve we have already talked about. The elliptical galaxies are actually sort of like if you plot them on the central surface brightness versus luminosity on the x-axis, they actually fall on a very tight line, right? So it's sort of a one parameter family. Luminosity, if you know the luminosity, you know the central brightness. In the same way, this is also very tight. The core radius size. So let me define what the core radius is. You have the surface brightness. Core radius is the radius at which the surface brightness value is half of its central value. So it's sort of some estimate of the size of the galaxy. So
like the half light radius in surface.
uh, yes, so there is also something called effective radius. Effective radius is what the half-light radius is. So effective radius is the radius within which you get half the light of that system. It's hard, the outer parts of these galaxies are extremely diffuse. To measure within what radius do you get half the light is tricky. But to measure uh, at what radius does the surface brightness reach some constant fraction of the central brightness is easier. So if you have that, and if you have like a model that goes through it, that's how you can actually connect the core radius and the effective radius. So it's sort of model dependent because the outer parts of these galaxies have a lot of stars, but it's very, you cannot measure the surface brightness there. Okay. And unlike these elliptical galaxies, which are like one parameter family, so luminosity essentially determines your size of the galaxy. The more luminous galaxies are bigger, right, from this, and the more luminous galaxies have lower central surface brightness from this. So they are essentially like HR diagram. This is like an HR diagram. If you know the mass of the star, you know its temperature, you know its luminosity. In the same way, elliptical galaxies have these tight correlations. Whereas if you put spirals on this, their distributions are not as tight. And this is for normal ellipticals, but then there are these dwarf ellipticals and so on. There's a lot of information in figures like this. Okay, so let's look at this. What is this? So this is an I band or V band surface brightness profile for two galaxies. This is a CD galaxy. Okay, let's sort of have a pop quiz. Which of these two is more luminous? NGC 1399 or NGC 596? Which is more luminous? Wrong. So luminous means total amount of light is larger. You see, it is brighter at the center, but luminosity is area under this curve. And you see these large, values at large areas. The area under the curve for this one will be higher than this one, even though it's bright at the center. In fact, this is what this plot is showing, right? It's bright. These galaxies are bright at the center, but their luminosities are less. Right, so this is a demonstration in terms of the profiles. And it's because of this extended thing. So that's why this diffuse outer parts of galaxies, which are extremely difficult to detect, can contain most of the luminosity of the galaxies. As Guru would tell you, this ICL has a lot of stars, intracluster light, extremely diffuse. It's very, very difficult to measure it. So its surface brightness is low, but it can actually have majority of luminosity of the galaxy. Okay, with this we are done. Cool. So this we talked about. So if I could, what's the time? 47. Okay. So about this stuff, so if you look at spirals and S0 galaxies, so it's sort of like an observational fact. So you see the shapes rounder than Q equals 0.2 with uniform probability. So basically, if you look at this graph that I showed, What I'm saying is this part, the flat part is entered where Q is equal to 0.2. So what it means is that the spiral galaxies true value is actually less than 0.2, because at the true value it sort of should rise up, and there are not a lot of them with apparent Q value less than 0.1. So most spiral galaxies have their true B by A between 0.1 and 0.2. By doing these statistics, this is the kind of things that you can actually learn. Um, what else? And there are very few galaxies which have Q less than 0.1. I mean, you don't have very extreme spiral, disky galaxies, very extreme oblate galaxies. So this is, you can do the same exercise for spirals as well. With spirals, you can actually think of as oblate, like extreme oblate objects. The other thing that you see is in elliptical galaxies, you don't have galaxies which are much flatter than E7. You remember En, this label at the E0 are spherical. E7 is, is quite it has a large ellipticity, and its Q value is 0.3, right? So you don't see a lot of galaxies which have the apparent Q value which is less than 0.3. So that means elliptical galaxies cannot be more oblate than 0.3, right? Why? So all these things actually are related to formation history and dynamics. It turns out if um, if an elliptical galaxy becomes too dominated by rotation, it can become unstable, and it sort of can reorganize into more spherical object. Similarly, if you have very anisotropic velocity distributions of stars, you can have dynamical instabilities which can reorient such things. So these observations have some implications for the dynamics of these systems. Okay, let's go back. As I said, this is something called an isophotal, a twisting isophote of an elliptical galaxy, and so to get twisted isophotes, you have to have triaxial galaxies. So the A and B and C are not equal to each other, and moreover, if you look at say this guy, this is rounder compared to the outer ellipse. So you can have the ellipticity, which is a function of distance. In that case, if you do the projection, you can have, say, this is sort of a cartoon of it. This is a viewing angle. And if you view from this angle, this orientation sort of more or less looks like in a similar. Since this is rounder, and depending on this angle, it can actually become oriented in the opposite direction. Here, the important thing is that B by A is a function of distance. It's not the same. So that's how you can actually get twisted isophotes. You can see the major axis is in this direction, and then it sort of twists to this. And this is a true example of that. So people have done these isophote modeling, like this is bread and butter in galaxy observations, photometric observations of galaxies. Okay, how do we characterize these boxy and disky galaxies? So here is these are the examples of. How do I get rid of this? Oops. So here is a disky galaxy. Here is a boxy galaxy. So this is how you sort of model, like quantitatively model boxy or disky galaxy. So this is one of these contours, like a model for one of these contours. So this is an ellipse which goes around through the middle of this isophote, right? So this is the best fitting ellipse for this boxy looking isophote. And what you will see is that at some angles phi, the isophote lies inside this ellipse. At some angles, other angles, it sort of lies outside this best fit ellipse, right? So the shape is not an ellipse. So how do we quantify it? what you can do is you can actually look at this uh, deviation value as a function of phi. Okay, so in this case, the deviation is negative at phi equal to 0. It's positive at phi equals 45 degrees. It again becomes negative at phi equals pi by 2. Uh, so this is that deviation delta. Okay, and you can actually write it as a Fourier sums in some sense. And what is so this sort of variation is like an m equal to 4 mode. You can actually see this is a cosine function, and so this is like a cos 4x, right? The whole way is done in pi by 2. This is cos 4x, and it has a delta value which is positive at 0. So which one would it correspond to? This one or this one? Here delta value is negative at phi equal to 0. So if the blue one corresponds to a boxy isophore, the red one corresponds to disky isophore. So A4, this coefficient of the fourth cos, cosine kt, k equal to 4, tells us whether it's boxy or disky. This is one quantitative way of doing it. So this is A4 less than 0, A4 greater than 0. So if A4 value is very negative, it's a very boxy isophore. Massive galaxies, more massive galaxies are giant ellipticals and so on are more boxy. Or sometimes they're also called peanut-shaped isophores or X-shaped isophores. And I mean, the isophore also reflects the dynamics, like what sort of orbits the stars have and things like that. So, by doing this modeling, we can actually get a sense of dynamics of the stars which compose this. So we'll actually come to that later. And there are like correlations. So this is a plot of radio power, radio luminosity as a function of A4. Recall, negative A4 is boxy. So let's see, negative A4, these are boxy orbits, and the radio power is higher, right, for these boxy guys compared to the disky guys, and they are more. The boxy guys are also more luminous. That's I told you, more massive galaxies are boxy, uh, so they host radio. Basically, this power is coming from black hole at the center, supermassive black hole at the center. Similarly, they also are luminous in X-rays. You can actually see a similar correlation. So there are a lot of such correlations, and the aim of galaxy studies is to actually understand them from more basic physics. Yeah, so here, what are the open circles? Yeah, so filled circles are guys with MB less than minus 19.5. So that means they are brighter. The filled circles are more luminous galaxies, and you can actually see the more luminous galaxies are more likely to host radio power and X-ray emission. So what about, okay, so this is great. How do you measure? So that was all about photometry of galaxies, like morphology. How does it look like in the images? What about spectroscopy? Right? If you recall, in our first or second lectures, we talked about this rotation curves, right? That if you take a look at H1 and go at larger and larger radii, you can measure for an external galaxy. You can measure this circular velocity as a function of distance. Can you do something like this for elliptical galaxies? Can you get a sense of whether elliptical galaxies have dark matter halos or not? How do you do that? Elliptical galaxies don't have a lot of rotation, right? How do you do it? So elliptical galaxies have one advantage. They don't have a lot of dust and obscuration because the cold gas is gone, dust is essentially not as much. And you can get the stellar spectra, which are essentially unabsorbed. If you can model those stellar spectra, then you can get a sense of this depth of the potential well of these systems. So here is an example of a composite spectrum of a galaxy. You remember this stellar population synthesis that I mentioned to you about? That stellar population synthesis is this way to figure out physical properties and history of a galaxy given the present day spectrum, SED, spectral energy distribution of a galaxy. So this is an SED for an elliptical galaxy. And you can actually see these absorption features, right? Stars have a lot of absorption. So these are stellar spectra. We actually also encountered this in one of our previous classes. And you have these, this is a more massive star. It has these higher ion lines. This is lower mass star. It has molecular bands and stuff. So this is a composite spectrum. So it's sort of a spectrum which is like an appropriate sum over all these spectra. And since these are red and dead systems, you won't have a lot of O stars. So these guys will be missing. Right? They've already evolved away. And so what you want to do is these individual features that you see here, right? This calcium feature and so on, you also see it in the sun-like stars one. But here, it's not coming from a single star. It's sum of all the stars in that galaxy with different velocities, right? All these different stars which have different line of sight velocities appropriately weighted give you these absorption features. So let me ask you a question. These features, whatever, these features that you have in this galaxy spectrum, would those be broader compared to an individual star or narrower? Why? Because of this random, right? Some stars are coming towards us, some are going away from us, and if you add all of them together, it's sort of like summing up all these narrow things with some spread in velocity. So it will be broadened. So this gives us a hint that the broadening of these features will tell us something about the line of sight velocity spread in the stars. So that sort of is the idea. So you take this composite spectrum and choose your line appropriately and look at the broadening of the line in these kind of spectra. And that gives you a sense of velocity dispersion of stars in a galaxy. Okay. So you'll have both. So you'll have this systematic shift and inherent broadening. Both of these things can actually be modeled. So okay. So this is an example. If we do this exercise for an elliptical galaxy, this is the velocity dispersion, right? So I said this SED, if you measure these absorption features, you can get a sense of dispersion, velocity dispersion of stars along the line of sight. So this is dispersion as a function of angle from the center. And you can see the value is sort of typical value is like 250 kilometer per second for this galaxy. Now this is radial velocity. Your elliptical galaxy can also have little bit of rotation. So you see here, the value here is 1450, but that's mainly the redshift. It's coming from the redshift part of it. But look at this, the radial velocity minus the systemic velocity. That's like your 50. And the rotation curve here has about 50 kilometer per second velocity, which is much less than the dispersion velocity. So that means these systems are dominated by random velocities rather than rotation, unlike spiral or disk galaxies. This is again, as I said, there are a lot of these correlations between different properties of. So this is rotation velocity divided by the dispersion of stars. So rotation velocity of stars divided by dispersion of stars. Each point here is a galaxy. You can do this exercise, right, for every galaxy and actually calculate the value of the rotation velocity and sigma. And this is how it looks like. These things which have these tails at the bottom are upper limits. Basically, V by sigma is less than this value. Okay. So what you see is the more massive galaxies, which are these filled ones, have lower rotation comparatively. They have lower rotational support compared to the less massive galaxies. Uh, and this is this A4 by A, right? This is disky, boxy business. So the negative values are boxy isophores, and you can more or less the boxy guys are the more massive ones, which are dark here. So, okay, so only last two slides actually. How much? What's the time? Okay, so I'll just take 5 more minutes because I want to be done with the elliptical galaxies. Okay, so all this is fine. Uh, Elliptical galaxies can also be used as a standard candle, right? Standard candles are very precious. Knowing distance in astronomy is very important. Okay, now how can you use elliptical galaxies as standard candles? So the idea is the following. Uh, if you just make a plot of velocity dispersion, so velocity dispersion is obtained from that sort of an exercise. You take the ACD, you see how much it has broadened and do all that, you get sigma as a function of angle or distance, and you sort of calculate some sort of an average, and that's here. This is sigma, and this is luminosity, say B band luminosity. And what you see is that the luminosity is sort of not very tightly, but correlated with velocity dispersion. Velocity dispersion is measurable, right? Now, how much far you put the galaxy, if you get its spectrum, you can measure the velocity dispersion. The x-axis is essentially luminosity. So if you're able to measure a velocity spectrum or sigma value of an elliptical galaxy, from this kind of a thing, you say, oh, so if this is the measured value of my sigma, this is the value of my luminosity. I measure the flux, I have the calibrated luminosity, and I know flux is luminosity by 4 pi d squared. I can get its distance. Right? So this can actually be used as a distance indicator. It's not as good as Cepheids and type 1As, but this is also used. So this is sort of like the rough scaling, which is shown here. The V band luminosity is proportional to the sigma, the velocity dispersion to the power of 4. This is sometimes called the Faber-Jackson relation in elliptical galaxies. A Faber-Jackson relation. Now it turns out you can make this relation tighter, and it looks like that this is like a projection of a more tighter relation in a space containing sigma, surface brightness, the central surface brightness, or the surface brightness within the effective radius, and the effective radius. Effective radius is the radius which the light of a galaxy. So this is called a fundamental plane. So imagine three axes along RE, IE, and sigma. They, in principle, they can be like, points can be randomly distributed. But it turns out that elliptical galaxies lie in a plane in this three-dimensional space. And that is called this fundamental plane. And this is the equation of that plane. Okay, if you use this sort of a relation and then plot velocity dispersion as a function of, so not velocity dispersion, but this sigma by IE to the 0.64, which you can actually on this. So sigma divided by IE by 0.64 as a function of RE, basically, you just normalize it appropriately. Then these galaxies, which are in Coma cluster. Coma is a nearby cluster at a known distance. So all the galaxies within this are at the same distance from us. Right? So these open circles have the same distance from us. And see, this relation has become much tighter than here. Right? So this can be a much better way of measuring distances. These filled circles are galaxies at different distances. So, they are not expected to be as tight. Now, these correlations actually tell us a lot about galaxy formation. And one of the aims of modern galaxy formation is actually to explain these in terms of their formation history, in terms of the physical dynamical processes. Okay, this is about. Okay, the other thing is this sigma at large radii. We know that the circular velocity at large radii in spiral galaxies or disk galaxies are dominated by dark matter. Right? That's how we know that there is dark matter in these galaxies. Here also, as you go to large distances, the the mass content is in dark matter. So it raises a very interesting point. The sigma squared, which is sort of the depth of the potential well. If you sort of assume virial theorem, right, the kinetic energy is minus half of the potential energy in a static, steady, gravitating system. So at large radii where dark matter dominates, you are measuring this sigma, but the luminosity is the stellar luminosity. And how come the dark matter and the stars sort of are sort of tight, their evolutions are tightly coupled, that the depth of the potential well tells us that this is the number of stars that you should form, right? So all these things are actually these correlations which tell us a lot about the physics of their evolution. Not only that, if you go to the very centers of these elliptical galaxies, a lot of them have these very massive black holes. Okay, and not just they have black holes, there are tight correlations between the black hole mass and this sigma value that we were talking about here. This sigma is not measured in the vicinity of the black hole. This is the same sigma of the large scale galaxy, which is much outside the sphere of influence of the black hole. And you can see that the black hole mass is proportional to sigma to the power of 4 or 5, something between 4 and 5. And these are M30, Milky Way, M32, M87. Milky Way and M87 black hole masses are absolutely beautifully observed, right? Event Horizon Telescope and the Nobel Prize winning work for Sagittarius A star. These are basically known. And you see the tight relation between the black hole mass and the dispersion, the radial velocity dispersion. Falls beautifully. Um, how do you measure these black hole masses? So in the case of galactic center, we could actually measure the Keplerian orbits, right? The Nobel Prize winning work. Now with Event Horizon Telescope, you actually can image it, and all that is fine. But before all this, and also for most systems, how do you measure it? The way to measure is again to go to these spectra. Look at these stars at the very center, which are near the sphere of influence of the black hole. The broadening of these absorption line becomes bigger and bigger, larger broadening. And that's because of the sphere of influence they're coming in the sphere of influence of the black hole. So their sigmas actually increase as they go closer to the black hole. If you look at the SEDs, spectral energy distribution closer to the black hole. So that's, using that and statistical sort of techniques, you can actually infer the depth of the potential well close to the black hole. That's how a lot of these things are actually measured. Right? A lot of these gray things are measured like that. They are statistical measurements from the SEDs. Yes. No, this is not like this is. We are not talking about few Schwarzschild radii. We are still like quite far away from very near the black hole. Okay, so the light will be dominated by large radii, not by the very center. Okay, so so we know the scale at which we're measuring sigma, and we know sigma squared should be some factor times gm by r. So we know the r because we know the distance of this galaxy. So we know the angle, we know the distance. So that's how you do it. But this is again a puzzle. Why should the black hole, which is so tiny, sitting at the center, uh, have anything to do with the depth of the potential well of the halo? Right? Sigma squared is essentially depth of the potential well of the halo, which is hundreds of kiloparsec. The sphere of influence of these black holes maximum is 100 parsec. And like in our case, the Milky Way case, it's 0.1 parsec. Now, how come this thing, which is like just 0.1 parsec is its sphere of influence, can sort of affect almost the whole galaxy? So that's like one of the puzzles. It's sort of like, uh, yeah. So these are some of the things, and it one of the reasons has to be feedback. Black hole and galaxy formation evolution is simultaneous, and it's governed by this feedback that I actually mentioned previously. Okay, so I think with this we are done with elliptical galaxy photometry and a little bit about uh, SEDs. Now we'll move on to spiral galaxies. Okay, thank you.